Oh, good. One of the good things about the presentation of good notes is it doesn't show weird text messages. All right. Okay. So, point here is for the audience here in the room, and anyone watching on Zoom, if they have questions to alert them. So please, if I go by something too fast, it's definitely something I've been known to do. You can stop me, say, hey, wait a second, by that. And so please don't. I hopefully set this up correctly such that you can access a folder where I'll put all my lecture notes in the stress bit.ly, EW Sydney. And the notes for today, which the only thing in that folder, you can get at this address, EW lecture 1. All right. So what am I going to talk about? My kind of aim here is to talk about the general theory of SL2 actions on categories, which is really a set of ideas, and to emphasize the applications of that in modular representation. So there are lots of other areas where you apply this stuff, and pretty much everything we'll talk about today will be general, but kind of what I'll try to emphasize is how you can use this to structure your understanding of representation theories, the symmetric groups, and related algebras. All right, but before that, before I explain categorical SL2 actions, I have to talk a little bit about just usual SL2 actions on vector spaces. So recall, SL2 is the Lie algebra of trace-free matrices. There are 3 parameters there, ABC, so it's 3-dimensional. And of course, there's a standard basis for E, F, and H. And they satisfy these famous relations. The bracket of E and F is H. E is an eigenvector of eigenvalue 2 for the bracket of H. So we say it has weight 2. F is an eigenvector of weight -2 for bracket of H. So we say it has weight -2. These are very important. They say that if I have a representation of this Lie algebra, and I diagonalize the action H, so representation where you can do that is called a weight module. Probably very few of you have looked at SL2 weight modules where H is not, SL2 representations where H is not diagonalizable, but they do exist. In that case, E will increase weight or H eigenvalue by 2, F will decrease weight by 2. That's something that's going to come up. Now, in this case where H is diagonalizable, you can actually think about my SL2 representations in a different way, which makes more sense for categorification. If any of you have ever seen, I'm not going to be talking about this stuff. People do it usually is sort of the first thing we sort of turn from thinking about SL2 modules where H is diagonalizable as integer eigenvalues to representations of an algebra where I have E and F and then a bunch of idempotents. Idempotents are called 1 sub n. And what they are is they're projections and bases. So for example, right, I don't need H here because I can write H as the sum of its eigenvalues times the projections to those eigenspaces. This is the spectral theorem for diagonalizable matrices. So I just can take E and F in this 1 sub n, and I can rewrite the relations of SL2 in terms of these generators. So before I said E, F, take bracket, I get H. Well, now this is if I take the commutator of E and F, and I multiply that by 1 sub n, I get n times 1 sub. It's projection to the n eigenspace, hx by multiplication by n. So this is just taking that equation on the left-hand side and multiplying by 1 sub n. And then these commutators of H with E and F say that when I compute a 1 sub n past an E, it increases by 2, and 1 sub n is 2. And when I compute a 1 sub n class F, I get 1 sub n minus 2. Okay, so no H. Why do I do this? It seems kind of a perverse thing to do. Maybe, yeah. But there actually is a good explanation, which is by doing this, I can make a basis that has positive structure. So you'll note here, writing these equations always involves a bunch of clicks. There's sort of no good way to rearrange things such that everything stays positive, because for any sl2 representation, there are always positive eigenspaces for H and negative eigenspaces for H. So it will always be impossible to write down a basis where H acts with positive structure. If I want sort of representation, I want elements in my algebra that have positive structure coefficients, I have to substitute it in H. And now this is okay. I have these projections can easily act positive structure coefficients.
And can't be negative. So in the first equation, be negative.
The first equation. This equation?
Yeah.
Yes, that's true. But you can rearrange. Well, this will be important. We'll get to it. Okay. So you see here, this is my basis that is going to have positive structure coefficients. So sometimes I take E times F, sometimes I take F times E, right? And that's exactly because of that. Sometimes it's positive. I'm sure I have this written many times lower down, but I can write this either as EF equals FE plus N1 or EF minus N sub N. So N sub N is equal to FE plus N. Right, and so if n is positive, I use this equation, and I want Fe. If n is negative, I use this equation. This is writing Fe as a positive linear combination of EF. So indeed, sort of because of this, trying to make everything positive, I have to use these formulas, and it depends that I take a higher power of E or a higher power of F. I think sometime, and I did it. Word for a moment, but this power with parentheses is what's called divided. It's to be divided by. Just sort of tends to make these formulas nicer. Right, so the positive structure coefficients here. These you can tell I copied these from a paper that was thinking about the quantum group, but just ignore the square brackets. Think of that as the usual binomial coefficient. Get the relations in SL2. And it's exactly sort of, it depends whether I have higher power F or higher power B. So this is all just kind of fussing with the relations. Okay. So why would it be important now? Really, that's not. You don't have a positive relations. You think that's good. But what I want to do is categorify the notion. I also thought I should probably try to explain what that is. So I'm going to consider an alien category. For my purposes, you could just say finite dimensional representation of a finite dimensional algebra. That's the only kind I like. All right, the Grothendieck group of this, see the usual definition. It's the free abelian group generated by classes of objects, modulo the relation that if I take the alternating sum along a short exact sequence, I get 0. On the other hand, if C is just an additive category, so the kind of thing you should think about is projectives over a given algebra, then the usual definition of the Grothendieck group is take all the objects in your category. Well, now we don't know how to talk about short exact sequence. Maps don't have to have kernels, so I just use the relation a direct sum of A and C. That's the same as adding the classes by A and C. There actually is sort of a unifying notion of exact split short exact sequences, the only short exact sequences. All right, so as I said, the most frequent thing that will happen for us is we'll have a finite dimensional algebra over a field K, and our category will be finite R modules. Right now. Yeah. So I can consider the category of finite dimensional R modules, and then the group lead group would be the free abelian group spanned by the symbols. And every other object I can has a simple solid, I can not out like that. And I can write it as a sum of like short partition series. On the other hand, I can look at the category indecomposable. Right? If I look at the category projective in group and be generated by the classes of the indecomposable projectives, and there's a bijection between these things. Every symbol has an indecomposable projective cover. Every indecomposable projective has a unique symbol motion. This uses finite dimensionality. This is really a property of which. There's an obvious map from the category projective, the shortly group vectors, the shortly group all R modules. Just take a projective, think about it as a general R module. I rewrite this in terms of the symbols. You can figure out how many times a symbol shows up in the composition series by looking at the dimension of from the projective cover. I probably need to be careful here if I'm taking a general finite dimensional algebra. So getting different division algebras, it's the end works my symbols, but let me don't worry about that, right? Let's just assume K is algebraically closed. So the inner work is very simple, just again. Not really going to want to assume this algebraic closure property because in the examples, like the representation of the symmetric group, there's no need for it. Do everything over at B. But sort of a few of these statements will be true about that. All right, so the matrix of this map in these two bases is exactly the matrix whose entries are the dimensions of columns between projectives, is what is called the Cartan matrix. So one interesting thing to note here is this map does not have to be a sequence. Probably in most cases, doesn't even have to be a nice. All right. So I have this group attached to every nice category. Now, well, I was talking about sl2 representations of sl2, so I'm going to need maps between these groups. So what's the kind of natural relationship between algebras that will give me a map between the groups? You might tend to say things something like a hum from one algebra to the other, but I think actually there's a better way to say this. Which is I should look at bimodules. So I'm sorry, I forgot to put the second algebra here. R prime bimodule. And the kind we'll want to consider is what are called suite. So these are bimodules. They're not projected as bimodules. I consider them as a left module or as a right module. They will be projected. So a great example of this is if I have a finite group and a subgroup, I can think of the group algebra of the whole group as a left bimodule over itself and a right module over the group algebra of the smaller group. And as a module over the group algebra of the smaller group, K of G is actually 3. It's index of H and G many copies of K of H itself. So this is an example of a suite bimodule. It's not projective as a K of G tensor K of H module, but it's projective as a K of G module and as a K of H module. All right, tensor product with a suite bi-module is always exact and sends projectives to projectives. So it both induces functors from R prime to R modules by tensoring, and from projective R prime modules, projective R modules. Straight line there. And the sort of example you should think about is, well, this one I introduced up above. If I think about tensoring K of G as a right K of G module and a left K of H module, what happens? Well, I keep the same underlying vector space, but I've now changed the group action. So this is actually a restriction from G modules to H modules. And I'll just note here, I can also write this as with the same Y module but plotted backwards. If I swap the order of those guys, I tensor a K of H module, K of G over K of H, that's the definition of induction representations of H. And whereas this equality on the top line is very easy, there's a not so obvious isomorphism from that induction, co-induction on the K of G.
Sorry, quick question.
Yeah.
On the second line of the example, left furthermost left term has an N, second one has an M, but no N.
Oh, I'm sorry.
I think that's an N.
That was a mistake. Yeah. Right. Okay, so because this functor is exact, sends short exact sequences, it's going to induce a map on K groups from the K group of R prime modules to the K group of R modules. And similarly, because it's in projectives, it induces a map of K groups to the projectives. And these are going to have positive structural coefficients. Okay, the matrix of these maps, in terms of the basis, I can write as the dimensions of Hom from projectives to other objects. One of them is Hom from projectives to the simples tensored with B, and the other one is Hom from B tensored with a projective to the simples. All of these numbers are positive or non-negative integers. B is the bimodule. The B is for any suite bimodule B, which have these non-negative integer structure. So if I have a map, and I'm going to turn it into one of these nice functors between modules over algebras, it better have positive structure. So for me, the definition of a categorification map, let's say for now between three abelian groups, of course, like if I had vector spaces, I'd be choosing three abelian groups inside them, is finding rings R and R prime, suite R prime R bimodule, which I showed you the name, B, such that for now, if we talk about projectives, the K group of R projectives is A, the K group of R prime projectives is A prime, and at my map applied to the class of an object is exactly the class of B tensored with that object or R. It's only happen if I found bases. So I want to do this to various different representations of SL2. And if I'm going to do that, I need to have everything have positive structure conditions. So the map H is never going to have nice categorification. So I'm never going to be able to find a basis where it has positive structure. But the maps E and F, there's no reason they shouldn't. All right. So as I said, we could kind of guess that a categorification of a representation of SL2 should be a categorification of E, H, and F, but that doesn't work. You can't get this positive structure. But we don't really need H. So I'd rather categorify the maps E, F, and one sub n. So what does it mean that I categorify one sub n? Well, it means that I have a category that corresponds to my S2 representation, but it actually breaks up into direct subs. One way to think about this is if if C is the projected modules over an algebra, then I can write that algebra as a direct sum of algebras, with my Cn being an algebras. So somehow actually I have a bunch of algebras for different integers, and then they're going to talk to each other because E and F, right, relate differently. So E and F are going to be functors from Cn to Cn plus 2, Cn to Cn minus 2. So if I think about it in terms of these algebras, it will be sweet binaries over these different algebras. And once we have this, well, we're really far along the road in SL2 actually. There's only one other relation. We need the relation that if we take E, the commutator of E and F, we act on something in Cn, we somehow get n times the negative. Now, as discussed before, having that commutator there is that multiplies. So I want to write this equation positively. And because n could be positive or negative, I actually need two forms of this equation. Right? I can either write at E plus n or E at minus n is equal to n. There's always this slightly awkward thing that if n is 0, then kind of neither of these equations is right, but actually both are right. Because things of weight 0, E f is just equal to n. All right. So written in terms of objects, this means if I apply the functor E f to an object, I should get, well, almost the functor f e. So if my functors were like, coming from a symmetric modular category, I expect that those two objects are isomorphic. But that's not what I expect. I expect there to be an extra number of copies of the object. But that's sort of a categorification of this relation. Again, let's just assume I'm working with projectives, so it's not so surprising that I get a direct sum. And similarly, if n is negative, then I get the E f of n. Well, it's almost fe, but I need to add another extra copies on the other side of the equation. See why I need this positive formulation. I can't write E f n directly minus n with a negative number of copies of n. Direct minus x. Okay. So I'll explain in a little moment why I think philosophically this is quite the right thing. But this condition, together with some other structures, gives a sort of good notion of categorical, which is what Chuang-Rouquier called strong sl2. So if I only have these relations, then we call that weak sl2. That gives you maps between the growth features that satisfy the relations of sl2. But you actually want something that's shown that gives you more structure.
Very bad.
Yes.
Is N a projective function? Or is it just A?
Okay, so. M does not have to be projected. Right there, so there are SL2 actions on abelian categories where N is not projected, but I still get this as.
Want this to be natural as a model?
So I'm not requiring that when I write this. This is exactly what I mean by philosophically a little odd. Is obviously it would be right to make this isomorphism natural. And I will explain how you can do that. But it makes my life slightly easier to not have to assume that I have particular in particular. So the examples I'm going to want to talk about those are the representations of symmetric groups over field of finite characters. And it's genuinely easier to prove this than to prove here is a particular map. And I know how to prove that, but it's genuinely hard. All right, so what's the actual definition? So this part is what I said before. So a category that breaks up into summands corresponding to the integers, such that each Cn is the finite dimensional modules, or I would say finite dimensional projective modules, for a direct sum of finite dimensional k-algebras. Now it's a little awkward to say direct sum of finite dimensional k-algebras. The reason I'm including that is when you think about the representations of Sn over field characters P, which is what an example, you don't want to think about one Sn. You want to think about them all at once. So you want to think about the representations of the algebra sum from n equals 0 up to infinity of ks. This is perfectly fine algebra. Because representations of the direct sum of the representation categories different SNs. So this is the kind of thing that I'm looking at. It's the direct sum of
There's no, you just wrote A, right? Yeah.
well, I mean, I could write it.
You still.
I'm somehow like what's going to happen with symmetric groups is there are going to be a bunch of different SL2 actions. And for each one of those, this direct sum A is going to break up in a different way into direct sum of ANs. And each one of those ANs is actually going to be a sum of finite dimensional functions. So it's going to be kind of a finite dimensional piece of each KSN, but it's going to be non-zero for ANs. All right. That's a good start. That's my weight position. That gives me the one slice. Now I'm going to have a pair of functors, EF. They're given my tensor product with sweep bimodules. And I want an extra condition for this. I want them to be adjoint. I'm specifically saying that EF is an adjoint pair. So E is the left adjoint of F, and F is the right adjoint of E. So I have this isomorphism of E and N to F. And since Alistair hasn't covered duality yet, I want to say a little bit more about adjunction.
Okay. Is the tensor product by sweep bimodules equivalent to saying the functors are exact?
Right. Because they are tensor product with sweep bimodules, they are exact.
But exact.
Sorry.
Could I just say that they're exact instead? Is that equivalent?
Yeah, probably. Again, once I know that you have the other way as well, then one of them being exact, the other ones those, and so speed. But I'm just, I'm putting these here in part because like, I'm not quite giving you the real full back definition. So it's a little easier if I assume some bias. And these are the only examples where we're going to talk. You can assume less and then prove as a theorem that the bias. Sweet, but why make life difficult first? Okay, so we're assuming that E after an adjoint pair of functors, that means I have this isomorphism of Hom spaces. There's a useful way to think about this, which is the important thing is where does the identity on EM go under this? It goes from the map of M to FEM. We're actually natural transformation from the identity functor to the functor M. It's called the unit of the adjunction. If you look at the identity of FM, that goes to a natural transformation from EF to the identity. So as an Alistair's talk, we're going to draw some pictures of this. So I'm going to draw E and F as a strand with an up arrow and a down arrow. Orientations help me keep track of which one is which. So if I read diagrams from bottom to top, this is the unit of the adjunction, is cup. So it goes from identity to F. Here I have a down arrow, here I have an up arrow, so that's what it's at. Similarly, this is the co-unit, it goes from EF. Note here, both the cup and the cap are pointed rightwards. Once I have these, it's easy to draw the picture of how the unit and the co-unit give you the isomorphism up here. Right, so if I have a Hom from N to EM, I can come here and attach the cup. That gets me a homomorphism from this is F and to N. So that's the map from left to right. On the other hand, here, the map from right to left, I start with sorry, I think I mixed my end. Sorry about that. I'll fix that. Anyways, here I have a map, and I attach the cup to it to switch from acting like that on the source to acting like EM. And then you get this usual picture of I want these inverse isomorphisms. That means that when I make this kind of S shape in the two ways that are possible with right with ups, I can then pull it tight and cancel the two units in a nice. Okay, so that was just kind of how you think about adjunctions. Now I need some extra conditions. It's not going to be enough to just have that. So this looks a little weird, but it's very powerful. I'm going to have an endomorphism E, which I'll call Y, draw as a dot on the string corresponding to that E, and I'll have an endomorphism I'll call psi, which goes from E squared to E squared. So, right, doing E twice is having two of these strings. And so if I have a Hom from E squared to E squared, it has to be a picture that connects two upward strings to two upward strings. And it's just arbitrary that I'm using a crossing. I could use some other crazy symbol. And maybe in view of the fact that Alistair used a crossing for the symmetry, it might have been better if I could come up with some other symbol, but it would make drawing pictures very possible. So these guys are going to satisfy some algebraic relations. And they are close to, but not the relations considered. Particularly this crossing, it squares in the identity, it squares 0. So I just want to emphasize this is very much not this nil version. So this is the usual symmetric group relation. Great relation, you might say. And here, this is how the dots and the crossings communicate with each other. When a dot tries to move across a crossing, well, they're almost equal, but there's this correction to be made. All right, so for now, this just looks like a strange set of relations. It's going to turn out to be really powerful. They do really naturally show up in representation, but at the moment they just look a little strange. One nice thing to think about, if I take a big power of E and look at all the different crossings of consecutive things, like the way that Alistair got the symmetric group from having the reversing map on just a pair of things, I get something that's called no where I told you the relations for kind of close together things, and then far apart things. So Alistair introduced the interchange law as something about modular categories, but it's not really about two categories. In particular, it's about have two functors and I compose them, I have natural transformations, do them in all right. I have this condition that I introduced before. I'm going to talk this to death now, but this is the sl2 relation. And then I have a couple of technical conditions I needed. So for any object, I look at E times that object, and Y acts on that. Right? It gives me a map Y from EM to EM. And I want that to be nil. Now, this is not saying that any particular power applies. In fact, in most interesting cases, in some interesting cases, there will be no power of Y that's zero in all objects. Certainly not required for each individual object, some power is. Because of all the finiteness conditions, COM from EM to EM is a finite dimensional algebra. So Y actually has to satisfy a finite degree of polynomial relation. I'm telling you that a linear relation is Y to symmetric. And if I act by a large enough power, but this is what's called integrability for representation of sl2.
Here, you're requiring this as markers given by
No.
That's
Okay, so if you had been paying attention, I'll spot that would bother me. That I said these two things are working without telling you how it works. Another way to say this is there should be kind of a universal category that describes this notion of an sl2 categorification. And this is possible, but it requires kind of changing things around. I gave you kind of the definition that's easiest to check in practice. When in fact, there's another one that's kind of philosophically better. So since I need to talk about categories, functors between categories, and then natural transformation between functors, I have 3 categorical levels I need to talk about 2 categories. So this would be this is very similar to the stuff that Alistair is doing, where you think of a monoidal category as a 2-category with 1 object. So a 2-category is really kind of a monoidal category where you're only allowed to tensor product certain things. Right? You have some label on the left and right of your objects that tell you, oh, you can compose these, you can't compose these. So when you think about that, you're like, oh, right, well, that's how you got a category from an algebra. But algebra actually only certain elements of these algebras. All right. So 2 category, the objects will be integers. So those correspond to these categories. Polymorphisms will be monomials E and And two morphisms are going to be cup and cap, and dot and crossing, that satisfy certain relations. Maybe I should just say, right, an sl2 categorification is going to be a representation of these two categories. It's a representation of these two categories, the two functor to the two category of categories, or categories with extra structure, let's say, B K linear. And that means that every object gets sent to a category, every one morphism gets sent to a functor, and every two morphism gets sent to an actual transformation. And so what this two category is doing is it's sort of storing the functors and the natural transformations and the relationships between them in a universal way in everything else. Okay. But the problem is I have these conditions D and E that several people very rightly objected to, which are not relations onto things. Right? These are not things I can express as something in my two. So I need some different version of these to be able to express this. And this is fixed by replacing D and E by another relation which does make sense two categorically, with a John called P prime, which is I write down a particular map from E times F to F times E plus n copies of the identity. And what is it? Well, I have a map from EF to FE by taking the crossing and sticking on cup and cap. So this is using my adjunction to turn the crossing, turn a map from F squared to F squared into a map from EF to F. As E and F is an adjoint pair, I can't do this the other way. I can't use it to get a map from FE to EF.
So we don't require E and F to be bi-adjoint.
No,
What do you do?
nothing changes. That's a redundant relation, it's a consequence of the other relations. I will explain that. Okay, so I only have a map from E and F to F. And similarly, I have a map from EF to the identity given by this cup. And there's sort of only one way to get more of those, which is I can take the cup and I can multiply it by dots. And so I just assume, well, if I take the correct number of those, so I take the cup times the dot times the dot times the dot, until I have the right number to get a match of the right thing, and I require this to be an expression. All right, and if n is negative, well, I do the only other thing. I move the copies of the identity to the other side of the equation. I only have one way to get a map from the identity to FE, it's this cap, and I have only one way to get more, which is to multiply by dots. So I do that for times. And I add in the relation that this guy is a nice I wrote the wrong map. So now we have a particular two morphism. We have the relation that this is a nice. And it sounds weird to say that that's a relation. What I really need is I've added a new generator, and then the relation that is the inverse of this. Right, so really I should have here added row and inverse as a generator. So this question about getting the adjunction the other way, this new inverse, that gets me a map the other way from FE to EF, FE to EF. One of the components of that is the adjunction the other way, the next FE. So this was a very clever argument, right? That there are kind of these different notions SL2 actually that were floating around the literature, but actually close. Weakest one, which is basically this one with B prime, and you can get that other there. So in particular, if you're used to the bottom and module, they have in the biojunction as another morphism, and then have a bunch of relations which are equivalent to writing down an inverse. Running low on time, but it's started a little bit late, so I think it's safe to do a few examples. So example one, it's very boring. All non-zero weight spaces are trivial. And C0 is K back, or actually I can take any category here I want as the degree 0 part. And I just declare that E and F are always 0. Now this is very boring, but everything works out, right? E and F are 0, so indeed they're adjoint. So the functor is adjoint to the 0 functor. And I have this decomposition. These endomorphisms are all 0. So of course they satisfy all these relations. And right on the 0 weight space, I have EF is isomorphic to FE. So this is when n is equal to 0. And of course, on the 0 weight space, I have because EF is 0. So I should emphasize here the 0 weight space is the only one where this trick works. I have a non-zero weight space. This relation tells me that one of E and F, actually both of E and F, have to be non-zero for some maps between weight spaces. Right? The right hand side here is non-zero, so the left hand side is. And indeed, right, this is also true for SL2 representations. Take any vector space and let E, F, and H act on it by 0, I'll get a representation of SL2. But if H acts by any non-zero, suddenly my life is. All right, let's do a slightly less trivial example, though it's pretty trivial. Now I'm going to take C1 and C minus 1 to be copies of vector spaces. And again, I could take any category as long as it's the same category. Okay, good. So on things of weight 1, F is the identity and E is 0. On things of weight minus 1, E is the identity, F is 0. Okay. And so now what happens? Well, on C1, I need to have that EF is isomorphic to the identity. Indeed, that's true. Right, the identity is adjoint to itself, and the co-unit of the adjunction is an isomorphism. On things of weight minus 1, well, the same thing happens but reverse. EF is 0, and the unit of the adjunction is an isomorphism. Okay, great. So there are non-trivial categorical SL2. This is not very non-trivial, but it's not as trivial as the first example. Since I'm running out of time, this is very convenient. Consider the algebra Ky mod y squared. This is a two-dimensional algebra that showed up in one spot as the endomorphisms as the center of S2. And I want you to check as an exercise that there's a categorical SL2 action where C2 and C minus 2 are both copies of vector spaces over the base field, but C0 is modules over this action. Again, it doesn't matter what they're with the functors E and F, being the only tensor products that make sense. I think you should be able to check by hand that this gives you a categorical. I'll maybe mention, since it connects to things on, actually, this is a special case of a categorical action on representations of GLN. Think of this C0 as the self-dual objects category of. Yes. It's but it's not the full principal block. If I wanted like projectives over the principal block, A module, like all A modules are projectives. This is actually sort of a special case. So this you can find this kind of actual representation here, and in fact, we get the same thing as the constructs expression.
Is there two categories for SLN?
Yes.
I can also do this co-invariant between modules thing. Well,
Okay, so I'm out of time. This is part of the question. The next thing I was going to do, which I guess we'll talk about next time, is there's a generalization of this sl2 emission, where instead of taking I can do a more general thing. I can look at the cohomology rings of cross lines. So I'm going to end up with a categorical action where C of L minus 2K, this is actually the Grassmannian, the cohomology of the Grassmannian of K length to L space. If I looked at in-step flag varieties, I would get categorical actions. And this is actually how Asilata found the relation. Yes, looking at the action. In the interest of time, I wasn't going to talk much about the higher end case, but it is relevant because, so for, the modular representation theory, which I'm talking about, representations of Sn over Fp, you get an SL2 action for every element of Fp. And those actually satisfy the relations of SLP act. So we're really getting a categorical action. It's after. But somehow for aligned applications, you don't really have to worry about different SL2s. Somehow all of the representation theory of higher rank Lie groups is in the fact that there are a bunch of SL2s inside them and how acting one SL2 changes the other SL2s. So that's all we really need. There is a generalization where sort of the important change is right here, instead of n, we say the weight lattice. Here, instead of just having one pair of functors, we have one pair for every simple root. They satisfy the SL2 relations, but then we also have endomorphisms between like EI and C. That gives you, that is just a representation. That kind of a representation. And making kind of that simple change, leaving all the other relations the same. This relation is purely an SL2. You get a categorical action that's higher.
In C, you put the Broué